Well, the first one's basically pretty simple. Did we do this one? That's all big. I am never going to teach a business calc class and a calc 1 class at the same time. It's too confusing for me. So if I plug stuff into there, what do I get? I get something like undefined over 1. Right? The tangent of pi over 2 is, well, wait, pi over 2 is where there's an asymptote. So it's undefined over 1 under. Whatever. And so then we need to figure out something else to do. The easiest thing to do with it is just to, I think personally, the easiest thing to do with it is to just say, well, tangent is sine over cosine, and secant is 1 over cosine. Oh, and now it's really easy, hopefully. If it's not really easy, then we can make it in a few more steps and make it really easy. So we've got sine of x over cosine x divided by 1 over cosine x. And then, of course, we'll flip that so we can multiply. And so we've got the limit as x approaches pi over 2 of sine x over cosine x times cosine x, which, of course, reduces very nicely to the limit as x approaches pi over 2 of sine x. And then we can just plug it in. And sine of pi over 2 is 0. So there we go.
Sine is 1?
Hmm?
No, cosine is the x and sine is y? So sine of pi over 2 would be 1? That is 0.
It's 0. That's why I did this little.
Oh, sorry. I was doing opposite.
I was doing the unit circle and
I was doing opposite way.
there's pi over 2. That's 0. That's the way, sorry, that's the way I do the unit circle. I've got to have that little action there to tell me where the, does seem kind of stupid, doesn't it? Let's look at the other one. Because why not? I don't think, this was definitely from a different calc book, because I don't think that we actually have these identities yet. But here's what you should do. Well, of course, the first thing you do is you say 1 minus cosine of 0 over sine of 0. So we've got 0 over 0. No, because cosine of 0 is 1.
We have 1 minus. Yeah, it's
Yeah.
0.
So it's 1 minus 1. Don't confuse me. So, undefined. And not only is it undefined, it's indeterminate. So that means it may or may not have a limit. So then we go, here's the little magic you do. You do this little magic. You multiply it by a very strange line. And unless you know the reason behind that, you would never do that. And then we've got the limit as x approaches 0 of 1 minus cosine x over x over the limit as x approaches 0 of sine x over x. Now, if you've got them memorized, which is about the only way to do it, you're going to know that this limit is 0, and this limit is 1. I think we've talked about this one, haven't we? Did we? Okay. Everything's really big for me today. So that means the limit as x approaches 0 of 1 minus cosine x over sine x is 0. Was there much trig stuff in the homework at all? Just a couple, right? Yeah, that's just so weird. Okay, so we did the next one in class. Did we do the following one? the factor using the cancellation theorem? Are you good with that one?
Yeah.
The next one, there was some funky math going on as people tried to do that one. So, and I was kind of leading you astray on that one too, so let's just do the easy way to do it. When we have fractional exponents, we tend to forget the rules that we're using. And so some of the things you were trying to do just won't work. So first thing we're going to do is we're going to plug it in, and we're going to say, well, infinity to the 7/2 minus infinity to the 8/3 is basically infinity minus infinity, which means it's one of the indeterminate forms, because you can't subtract infinities. Well, some of them you can, some of them you can't. I know, it's really wacky. But anyway, it's indeterminate. So, now I got a common denominator, which I did tell you to do, but then I kind of led astray after that. So what we're trying to do here, and it doesn't, what does it say? Oh yeah, it does. It says factor and use infinity times infinity. So that must kind of give you a clue that what you're trying to do is get infinity times infinity. Okay, so factoring means let's factor this out of the expression. 16/6, x to the 16/6. So if I factor x to the 16/6 out of here, this will be x to the 5/6 minus 1. If I were to give you one like this on an exam, it would not be fractional exponents, because even I was kind of like, oh, fractional exponents, what do you do with those things? You use the same factoring rules, but it's just kind of, it doesn't feel quite right most of the time. So now, when I plug infinity over infinity in there, I get infinity times infinity minus 1, which is infinity, whoops, times infinity, which is fine. And so then infinity times infinity is infinity. Some of the ways to remember when you can do addition, when you can do operations with infinity, is if you think about the fact that addition and multiplication are the good operations. They're the ones that you don't have to have special little rules for. Like division, you have to have the special little rule about the denominator can't be 0. Subtraction is neither associative nor commutative, which means that order matters. 3 minus 2 is not the same as 2 minus 3. So it's kind of the same idea. If you stay in the good operations of at least the first 4, then you're fine. So you can multiply infinities and you can add infinities and you still get infinity. But if you try to subtract infinities, you have no clue what you've got. And if you try to divide infinities, you have no clue what you've got, because those are the bad operations. And maybe that doesn't help, but hopefully it does. I don't know. So how about rationalize with the conjugate? Was that one okay? As long as you didn't multiply the denominators together so that you couldn't reduce. Good, bad, want to do it?
Want to do it?
So when we were taught to simplify rational expressions, we were trying to simplify the denominator, to get the denominator as nice as possible. Well, in calculus, generally what we do is we're trying to get the numerator niced up, hoping that if we nice up the numerator, we can reduce and maybe not even have a denominator, which would be lovely. But that's, so we're nicing up a different thing than we did in algebra. So if we want to nice up the top, we'll multiply by its conjugate, which is square root of x plus 4. Remember, conjugate is same leading term, same trailing term, signs are different. It's the difference of squares pattern. Oh, I forgot to plug 16 in and show you that it was indeterminate. There we go. I plugged it in my head. Don't do that on, you should always show that you plugged it in. Because that should always be your first step in finding limits. Plug it in and see if I get a value out of it. Oh, so what have we got here? Let's see, that'll be square root, that'll be x minus 16 over x minus 16 times square root x plus 4. And what do you know? Very lovely there. That reduces out to 1. And so I have the limit as x approaches 16 of 1 over square root x. And then I can just plug it in. Get 1 over square root 16 plus 4. So how come I can reduce? How come I can change one function into another function?
Is this the same function minus the discontinuity, or minus the whole?
Minus the whole, right. The whole the whole in the function discontinuity. And that's really important. We can just take the whole out because then we know that the functions are the same except for that one place. And that one place is kind of nice. So they're the same function other than at that one little tiny place. How about the next one? That one was just algebra, really. Did you want me to go through that one? Yes, no, maybe. I don't care. I just want to hold it bed. Oh, wait, that's me. Limit as x approaches 0. Have I apologized to you about Word and the fact that Word doesn't like to put x approaches anything underneath limit, and half the time it does and half the time it doesn't? Not my fault. I've tried to fix it, and every time I try to fix it, it just goes wonky, so I quit trying. So first thing we do is plug it in. And we're going to have 5 over 0 minus 5 over 0. So that's infinity minus infinity, which is, I don't know what to do with that. It's indeterminate. So I've got to go back and do some algebra. And most of the time, when you come up with indeterminate, that's what you're going to head for. You're going to head for, let's just do some algebra. Let's kind of try to simplify this rational function so that it makes a little more sense. I think common denominator would be a good idea. And I know I'm kind of going fast on this, but my expectation is that even though my algebra goes faster than yours, you can follow it. And so then what are we going to have? We're going to have the limit as x approaches 0 of 5x plus 5 over x times x plus 1 minus 5 over x plus, whoa, that's a pretty x. So we've got 5x plus 5 minus 5 over that common denominator. And so we've got 5x over x times x plus 1. And there we go. That'll help us out a lot. And so now we've got the limit as x approaches 0 of 1 over x plus 1. And so now we just plug 0 in. And our limit is 1.
How did you get 1? memory.
Is it supposed to be 5?
Yeah, it's supposed to be 5.